So in the last video, we talked about how you have a higher concentration of potassium on the inside, around 150 millimoles per liter, than you do on the outside, let's say around 5 millimoles per liter. So, and just to recap some of the kind of important points we brought up, we said that essentially what happens is that you have these potassiums that are bound to little anions that are the green dots there. And because the concentration gradient is going to want to make the potassium leave the cell, it will. And so it'll leave the cell. Let's say this little fellow will leave the cell here, and he'll end up on the outside. So by doing that, he leaves that anion all by itself. And if this continues to happen, then these anions create this negative charge, and we can actually figure out exactly what that negative charge is. It turns out that that negative charge is going to attract back the potassium, right? We said that this potassium then is going to want to kind of swim back inside to be closer to that negative charge. And this is kind of that interesting idea, the idea that K leaves behind a negative charge and then comes right back and wants to be by that negative charge. And the amount of negative charge that's going to offset the concentration gradient is around negative 92. So let me write that in now. So negative 92 is the amount we know that we need to kind of offset the concentration gradient. So that's where we left off. And now I want to do a little thought experiment. Let's say that we come at this cell with a little injection full of, let's say, some positive charge. And try to ignore the kind of ridiculousness of what I'm saying just for the moment. But just focus on the positive charge. The fact that I'm going to pour a bunch of positive charge into this cell. And let's assume that we don't know exactly where this is coming from, but that this positive charge is essentially what it's going to do is it's going to make my cell not negative 92 anymore, right? It's going to make it more positive than it is. Let's say I make it, let's say halfway back to 0. So instead of negative 92, it's negative 46 millivolts. So this is the new membrane potential, right? And our cell is still just permeable to potassium, and that's really important. It's only permeable to one ion, that's potassium. So what's going to happen? Well, these potassiums, these little guys right here, they're going to notice that the charge is actually not drawing them back as strong as it was before. So this potassium might see that and it might leave. And so more potassium basically starts leaving the cell. And if more potassium is leaving and kind of going on the outside, then you have more of these little anions that are left behind, and the process continues, right? So these anions say, well, you know, if we're off by ourselves, we're going to contribute to this negative charge. We're going to add to it just as it did before. And that negative 46 is quickly going to go down again. It's going to slide back down. And the question is, how far does it slide down? Well, it goes back to the equilibrium point. So if we said negative 92 is what you need to make this yellow squiggly attraction, the membrane potential, equal the concentration gradient, if that's what's needed, then it will slide back down to negative 92. So think about that for a second. It's pretty powerful stuff. I mean, you can do all sorts of kind of funky things to the cell. You can add positive charge or negative charge, and as long as you maintain two important things, one of them being the concentration gradient. So one is this concentration gradient of 150 versus just 5. That's one thing. And the other is the permeability to only potassium. As long as you maintain the permeability, you'll get back to negative 92. So actually, let me even hammer this point harder by showing you a little diagram. So let's say we have a concentration gradient over here, and I also have permeability over here. Permeability. And this is permeability to potassium, okay? And assuming that we only have permeability. So assume, I'll write that very clearly, the cell is only permeable to one ion, only one ion. So assume only one ion for this permeability. So if you have, let's say, permeability yes and permeability no, and you have concentration gradient yes and concentration gradient no, then what do you get exactly? So let's say you have 4 possibilities here, right? We have 4 possibilities. And let's say we have no concentration gradient and no permeability. Would we get a membrane potential? Well, no, because the potassium would never have a way of leaving in the first place, and would have no desire to leave. Now, what if you have concentration gradient, so you have the desire to leave, but you don't have a way for that potassium to actually leave the cell? Well, again, you don't actually have any membrane potential. And the same is true as if you have, a permeability, but you have no concentration gradient. Then the potassium, again, has no desire to actually leave. And then finally, if you have permeability and a concentration gradient, then you actually get down to your negative 92 millivolts. So concentration gradient is kind of when I use the word desire. Does the potassium have a desire to leave? And permeability is, does it have a means? Does it have a way to leave? So these are the two things to kind of think about when you're thinking about whether you would create a membrane potential or not. So if we have that set up, let's actually move down a little bit, make some space, and actually talk about how you actually get your negative 92. Where in the world does that number exactly come from? So there is a formula, and that formula is, I'm going to write it out over here. It's Vm, and all that means is membrane potential. Now, if you're like me, the first thing you notice is that there's no V, there's no letter V in the word membrane or potential, so how do they come up with that? And I don't know the answer to that. I don't know where the V comes from exactly, but Vm stands for membrane potential, and the formula is actually surprisingly simple. It's 61.5, and this is kind of a simplified version because there are a lot of constants in here that get kind of thrown together in that 61.5. And you just take the log of the concentration of potassium on the outside, I'll say K out, potassium on the outside, over the concentration of potassium on the inside of the cell. So you take these two concentrations and you get this fantastic little formula. And you can actually, now I can write for you potassium over here we said was equal to negative 92 millivolts, so that would be the membrane potential. This is the membrane potential. And I can even walk through a few other ones, some other key ones. So there's sodium, there's, let's do chloride and calcium. So a few of them, and all of them have the same kind of formula. You just take their concentrations on the inside and outside and plug it into the formula, and you get positive 67 for sodium. You get negative 86 for chloride, and you get positive 123 for calcium. And now keep in mind calcium has a 2+ charge. So for calcium, this 61.5 actually gets changed to 30.75. And that's rounded off. But that's because of that 2 positive charge. And all you do is, as I said, throw in the concentrations on the inside and outside. So actually let's even write that down. So concentration gradient, and keep in mind exactly which way things are moving. So concentration gradient for potassium, I mean, really you're looking at a positive ion, right? That's moving out of the cell. And for sodium, you have a positive ion, but it's moving into the cell. For chloride, you have a negative ion moving into the cell. And for calcium, you have a positive ion moving into the cell, really just like sodium. So this is how you kind of can think about the 4 major ions that contribute to our cell's membrane potentials.